Okay, so this last problem is on the diffusion equation. This is the diffusion equation, and in class we've been treating this as a linear shift invariant system. We derived the transfer function for this linear shift invariant system. Now keep in mind, here the variable is really x, right, or position. It has a corresponding frequency variable or spatial frequency variable of s. S is in Sam. Okay, and so this is the Fourier transform relation that we use. Okay, and so now you're asked, assume that the initial concentration is given by f of x comma 0, that's the initial condition, is equal to something 1/2 plus 1/2 times a cosine, and now this cosine, the picture is it's a periodic function in space, right, or position, no longer in time. But that doesn't bother us, right, because we have our transfer function as a function is in terms of spatial frequency. Okay, and so the linear shift invariant system we derived corresponding to that differential equation was that the initial condition convolved with the impulse response gives us the condition at some later time t. It gives us the concentration at some later time t. So we could solve this problem doing a convolution. Okay, that would be probably the more difficult way to solve it. Another way to solve it, right, is to remember that for a linear shift invariant system, if we put in, let's write it like this. So if we put in a complex exponential, so j2 pi s naught x, right, through a linear shift invariant system, what we're going to get out is the transfer function, so this would be h sub t of s naught times the complex exponential. Okay, remember, so this was the property that complex exponentials are eigenfunctions of linear shift invariant systems. No longer time, right, because we're now dealing with frequency, spatial frequency and space. Okay, so the corollary of this is that if we put a cosine through a linear shift invariant system, what we get out is another cosine that's phase shifted by the phase of the transfer function, and that's scaled in amplitude by the amplitude of the transfer function at the frequency of the cosine, right? And then the frequency of the cosine itself doesn't change, right? So s naught came in, frequency s naught, spatial frequency s naught, spatial frequency s naught comes out. Okay, so just looking at these two, we can actually already solve this problem, right? Because let's look at what we have. We have a constant, right? But a constant is just a complex exponential with a 0 frequency, right? And then we have a cosine at spatial frequency of 1, right, which is the second property that I wrote. So we can actually almost write the answer by inspection. Okay, we have the sum of two terms at the input, whose output we know, and so we can just sum the corresponding outputs. That's what linearity means. So what are the corresponding outputs? Well, the 1/2 is, you can think of it as a complex exponential with s naught equals 0, right? Or you can think of it as a cosine with s naught equals 0. But in either case, what you're going to get is that the constant, right, or the constant term, that constant offset, is going to come out of the linear shift invariant system scaled by h sub t of s naught, which is 0. The second term, the cosine, is going to come out scaled by h sub t of 1. And phase shifted by the angle of the transfer, or the phase of the transfer function at 1, s naught equals 1. Okay, so that's it, we're done. So h sub t of 0, let's look at our transfer function. That is equal to 1. And then h sub t evaluated at 1, well, that's equal to e to minus 4 pi squared t. And the phase is always equal to 0, because this is a real number, or it's a real and positive number. Okay, so this is equal to 1/2 plus 1/2 h sub t of 1 e to the minus 4 pi squared t cosine 2 pi x, and then of course this is 0, right? Zero-degree phase shift. All right, so that's how you get the solution. Part B, what is the limit as t goes to infinity? The limit as t goes to infinity, well, as t goes to infinity, this term becomes very small, and so the limit as t goes to infinity of f of x and t is equal to 1/2. Okay, so if we think about the diffusion equation, what happened was we started out, this is our offset of 1/2. We started out with these oscillations like this, right, in concentration. And then what happened was we had diffusion, or net flux, down the concentration gradients, and that tends to smooth out the these variations, right? And then as we let t go to infinity, actually what we're left with is just this average concentration, right? So nothing is created or destroyed, but these initial spatial variations are all smoothed out by diffusion. Okay, and that's what the math shows in the end. Okay, so there's another approach which is shown in the solutions, which you can also go through, which should help. Okay, but this is problem 5.